Cool, thank you. Well, I would like to start by thanking the organisers for introducing the intellectual abstract category, because we actually submitted this as an intellectual abstract, but the PC decided this wasn't intellectual, so we're just regular. So let me start by explaining the title. So, weight-free weak reference counting. So I'm going to start with the easiest part for this audience, reference counting. So hopefully everyone knows what that is. It's where you count the number of incoming edges. So you take a tree and have a couple of pointers into it. So here we've got, oops, that's the wrong thing. Basically kind of counts next to things for how many edges are coming in. Sorry, that was, so then if it goes away, that will go down, and then we can say, oh, we'll collect that object, and then we remove stuff, and it's all great. Reference counting, awesome, apart from cycles. So with cycles, it gets a bit harder. So here's the same tree again, but now we've got parent pointers. And if we did the same thing now with this tree with parent pointers, when we take away the edge, this reference count is 2 because there's pointers coming up to it from below. So that's not so great. So then we move on, and we've now got this completely unreachable piece of memory, and it's not going to get collected. So that's where the second part of the title comes from, the middle word, weak. So often you find in reference counted systems, you get strong and weak references. So a strong reference actually prevents the object going away. A weak reference allows you to access it if there's a strong reference to it. So in this kind of, if you have basically weak references on any cycle, then you're not going to get leaks. So as long as there's a weak reference that breaks any cycle, you're good. So if we go back to the tree example, now we've got these pointers back up for weak references. So we've got weak references going as parent pointers and strong references going down. So if we do this, we take away a strong reference, that gets collected, it calls the destructors on the removing the pointers, and now this object here has a reference count of 0, so it can run its destructor as well, so it removes its weak reference, and then it goes away. But this top object can't be deallocated because it's still got a weak reference to it, but it has run its destructor. And this means that you can't actually use that weak reference to access the object. It's just kind of hanging around to keep it safe. So if you ever follow this pointer, you've got something, you're not touching dangling memory. So that's 3 of the 5 words in the title. So the remaining bit is weight-free. So weight-free is a progress property. So you have, in concurrent data structures, you often say how well it's going to make progress. So you have sort of on one extreme blocking. So this is when a data structure won't make necessarily progress unless basically something else completes. It won't actually be able to make progress. It can be blocked by something. And on the other extreme, you've got weight-free, which is kind of the best kind of concurrency, which is no matter what happens from the environment, it's guaranteed to make progress and terminate. So there's no way in which like any schedule can stop it finishing. So that's kind of great. It means you can't do things like spinning, or you can't even do cast loops typically, because if you do a cast loop, you don't know why it's going to terminate. So basically any looping is pretty tricky to fit into weight-free. So why is this a problem? So if we look at actually what's going on inside the reference counting mechanism when we want to do reference counting with strong and weak references, what we've got here is this basically a sort of state machine. So your strong reference count goes up and down as you do increments and decrements of a reference count, and when it hits 0, you can run the destructor. So once you go down here, you can run the destructor. And importantly, this edge doesn't exist, right? There isn't an edge going back. That's not allowed. So that's kind of really important because you don't want to hit the destructor more than once. You can only run a destructor once. And also importantly, when you go down to this sort of last step, you actually hold a weak reference typically, right? There's sort of one weak reference inside the system which is given to you when you're the last one out. So you can know that the object where you're going to run a destructor on doesn't disappear. So this kind of all works in terms of strong references, but when you do the weak reference promotion, what you have to do is effectively an increment, but you don't know if there's a strong reference or not. So if you just did an increment and you didn't know if there's a strong reference, you'd actually be adding this edge in. So you have to do something slightly more complicated. So if you take the sort of standard example you see in the C++ runtime standard library, what you find is there's a loop in there. And that loop is going to basically try and add the reference count on and then do a compare and exchange. So if it's not 0, try and add it. And if it's not 0, try and add it. And it will keep doing that until it succeeds, because something could run in this little gap here that happens to change the reference count on that object. So if something, every single time you went round there, changed the reference count, you would never actually complete your promotion. So this is why this isn't wait-free. So if we run some benchmarking just to see this, so this is like the worst case possible thing you could do. So it's a tight loop trying to promote in every thread on the machine. So we've got it was a 72 core box, which had, 72 hardware threads, so 36 cores. And you see that basically you get this getting really bad as you add more threads, it gets worse and worse. And this is because it's kind of keeps knocking threads out of progress properties, so they keep knocking away. Okay. So what's the solution to this? So we're going to take this same kind of idea. So we've got the strong reference counts, and they're going 0, 1, etc. But what we'd like to do is have this edge here, because then we could use increment rather than a cast loop. Now, if we add this increment in, this means we can reach here multiple times. So every time we hit strong 0, we can't just run a destructor. We need to do something more. And because we kind of get a weak reference count when we go from 1 to 0, we need to give one back when we go the other way. So we need to actually say we're going to have to give back a reference count in however we design our algorithm. And because we can reach this multiple times, we need another step in the algorithm to actually work out when we can close the reference count. So the reference count at the moment, if we hit strong 0, that isn't saying we should run a destructor. What we're going to do is add an extra state, closed. And this state is basically when you go to strong 0, you try to close the reference count. And what we want is some way in which we can do this such that we can perform an increment on closed and it stays there. And if we perform an increment on strong 0, then it moves to strong 1. So this means we've got effectively sort of two states where we're closing it out. So it goes to strong 0 and then to closed. But something could come along and block us going into closed. So our operation there might end up not necessarily happening because someone increments it away, right? So we can actually step out of that state. So we can actually represent this really nicely. So there's actually a way of representing this just with our standard 64-bit kind of reference count thing. What we're going to do is have a 63-bit reference count. So strong 0, strong 1, etc. are going to be represented by 2 to the x, where x is the strong number of strong. So strong 0 is represented by 0, strong 1 is represented by 2, etc. And closed can just be any odd number. So we pick any odd number, and that's what we're going to represent closed as. So in particular, this operation where we go from strong 0 to strong 1 can just be an operation that goes, is it 0? Yes, make it 1. And then that's a perfectly valid way of doing that, and that's a CAS. If that CAS fails, it's fine because it means someone's already moved it away from strong 0. And all our increments now become add 2s. So as long as we have fetch and add 2, then we can do in graph as +2, because if it was odd, it's going to stay odd when we add 2. And if it was even, it will stay even when we add 2. So it gets us, this entire state machine can be done now just with adds and a CAS that is allowed to fail, and we just back out of saying it's closed. So if we do this, we can build code. The paper has all the code in, all the examples. But we can run that example we had before where we do a tight loop trying to do promotions. And this red one is the original algorithm. And now with the wait-free one, we see we don't get this bad behavior when we hit kind of higher thread counts. So what can happen now is it just will make progress. And that's kind of much nicer. Now, it isn't all clean sailing. There are worse cases. Because this algorithm, right, has a two-step closing process. So if we're trying to close the reference count in a tight loop, then actually we're going to be worse. So here we've got an example that does a tight loop of allocating an object and then dropping the reference count. So if we do that one, then when we're a classic algorithm, we're the red blocks here, and then the weight-free ones are slower. So we've made it worse in the case where you just allocate a reference count and drop the reference count straight away. So that's basically what I'm going to present. So in the paper, we've got all the code, all the benchmarks. There's an artifact we've created on GitHub, which you can go and find all this code, all the benchmarks, all the performance analysis. We've got an optimized version of the algorithm in the paper. So the original algorithm kind of behaved nicely if you were going down from 1 to 0, but didn't behave nicely if you got weak references around. So what we've got here is effectively in the paper, there's a version that's got both state diagrams kind of smushed together with extra edges in and even more complexity, but it works out as giving you, it gives you a much better worst cases. So in particular, this worst case goes away if we do the optimized algorithm. It is ever so slightly worse, but not much. We've also got in the paper a bunch of CDF-like properties of the various thread counts for the promotion, so you can look at kind of how the system changes and more graphs. And I particularly found out about violin plots when writing this paper, so I did some of those because I really liked them. Something that else that's in the paper is actually we verified it all. So there's this tool, Starling, which I worked on with some other people, so Matt Windsor, Mike Dodds, and Ben Simner about 5 years ago, which does verification of programs kind of using a separation logic-like reasoning system, automated. So we pushed the weight-free algorithm and the weight-free optimized algorithm through that verification tool and verified actually the code does what it says. Weight-free was kind of easy because you can just look at the code and see completely obviously that it's weight-free because there's no loops anymore. Cool, and I think I might be a bit short on time. Questions?
Why did you think this was an experience paper?
Intellectual abstract.
Sorry, intellectual. What we call intellectual?
So because we don't have a compelling use case. So I've got micro benchmarks that we could sort of demonstrate stuff, but I didn't feel we'd got the sort of like that big industrial, like, here's why you want to do it. So in that sense, this is an intellectual curiosity. It's like, it's an interesting step, not a...
Why don't you have non-micro benchmarks?
So why don't we have non-micro benchmarks? So it's...
Is this used in Rust?
Yeah, so Rust has a version of this. The thing that I've struggled to find is any example which has heavy use of weak reference counts and concurrency. So there's a lot of places that use weak reference counts, but actually where it's contended is a case that I haven't managed to find any benchmarks for. So if it's not a contended weak reference count promotion, then the numbers aren't going to be noticeable. So that's the thing I need to find. So if anyone in this room has an example like that, I'd be really happy. But otherwise, it's, yeah.
Any other questions?
It's Tony is walking there. So Rust has arc, which doesn't have weak, does it?
You have
Yeah.
to repeat the question also.
I can...
Never mind.
I guess I'll ask first. So I have two small questions. So the first is, do you know of any data structures where applying this version of RC actually improves its progress guarantee? Because originally it will need to depend on a log-free RC, but now since you made a weight-free RC, you can use a weight-free RC.
So I don't know if, I don't know of any. So if So most of the places where I've seen the weak reference count used is sort of like in promotion of like you might have a context that's shared, so then you have a weak reference to it. So in those cases, you get a better progress guarantee, but there's so much other system around, like it depends really what's going on elsewhere. So I haven't sort of thought about it in terms of specific data structures, because then if you're swinging pointers around, you've got all kinds of operations you need to do to make reference counting actually concurrency safe. So again, there's a bunch of papers on doing that sort of in a more general setting. This was really looking at just at the kind of implementation you'd get inside the STL or inside the Rust standard library, and changing that.
I have a second question. So you mentioned that you also have verified information. So have you verified the weight freedom inside the star framework, or is that done separately?
So we haven't automatically or mechanically verified weight freedom at all. The code has no loops in it.
Jim, do you want to ask a question?
I forgot.
Any other questions? Otherwise, thank you, Matthew.